Kuhn thought that a lot of what was most important in guiding a scientist and telling them what to do every day when they turn up at the lab or the observatory or whatever, is stuff that's always specific to a particular paradigm. The way actually Kuhn put it in a quite inspired, quite extreme metaphor was it was almost as though the paradigm turned science for any particular, a scientist, the paradigm for some particular field turns the scientists in that field into puzzle solvers, as though they're being presented with something like a crossword puzzle or a Sudoku or something like that, where the rules are very clear, the framework is very clear. It's just a matter of trying as hard as you can to follow the rules and get the little bits into the right places.
Hello, this is Robinson Earhart here with the introduction to Robinson's podcast number 126. And this episode constitutes the second part of a back-to-back philosophy of science bonanza, this time with Michael Strevens, who is professor of philosophy at New York University. And Michael works broadly, I think it's safe to say, across the philosophy of science, and has written on complexity, probability, the philosophical applications of cognitive science, and many other things that I'm not mentioning. But in this episode, we talk about Michael's recent book, The Knowledge Machine, which explores, among a number of other things, how irrationality, which we don't typically associate with good science, how it shaped the scientific revolution and the dawn of what we now think of as science today. Along the way, or maybe as we start at least, we get into what Michael calls the great debate over the nature of the scientific method, where we get into some of the work of Karl Popper and Thomas Kuhn, which you might already be familiar with. And then we focus on the way explanations work in science, with particular attention to the role of objective evidence on the one hand, and on the other, factors like religion and aesthetics, which Michael thinks do have a role, or maybe even, I don't want to put a word into his mouth. I was going to say ought to have a role in the way that scientists think, but which don't belong in public argumentation. We finish then by talking about good old I can't get a word out today. Good old pseudoscience, which has become a friend to the show of late, and then its relationship to Michael's project. So there are links to Michael's website and his book in the description, so you can see what he's up to, and you can also check out The Knowledge Machine. And comments, subscribes, likes, they make pins, which is the podcast's name, and I very, very happy. So smash all those buttons that you have access to. And now, without any further ado, I hope you enjoy this conversation as much as I enjoyed having it with Michael. A natural place to start, I think, is why you decided to write The Knowledge Machine in the first place, because much of your other work is, I think, quite technical or technical adjacent, in so much as complexity and probability aren't obviously popular subjects. So what made it seem so timely for you to write about the scientific method and the core of science, and in a much more accessible way than you might a philosophical journal article?
Yeah, well, probably I'm not an expert on all of my motives for doing it, but the one that I think is really salient to me is that I had some things I wanted to say about science that had come out of work that actually was quite technical in confirmation theory, but that I thought actually would suit the general audience format better, because it was going to be a take on science that was philosophical, but also sociological and historical and so on. It was going to be quite multidisciplinary. It is quite multidisciplinary. And I felt that an academic treatment would be just too ponderous. So it would be too unwieldy to kind of bring all that stuff in an appropriate kind of wheeling in all the academic machinery for all of those different disciplines. It would actually work better as a kind of a lighter, faster moving story. And of course, I mean, it loses something because of that in terms of documentation and citation and integration into the context. But it means that in 200-300 pages, I can really kind of give an overview of the picture I had in a way that I hopefully is really accessible and engaging, not only to ordinary readers, but also to my colleagues in philosophy and philosophy of science in particular.
Mm-hmm. And I know it's been really well received among philosophers. Barry Lower was actually who told me about the book, and that's how I decided I really want to talk to Michael about it. But the sociological and historical elements that you weave into the knowledge machine, I think they really do bring the philosophy down to earth, and they also serve as great examples for giving the philosophy roots, so to speak, something to grab onto. But I find the title, the knowledge machine, very neat, or rather, I guess what underlies the title, the conception of science as a machine, that it's something we use to produce something. And of course, I mean, science is abstract, but what the title suggests is that it's something reproducible, that like a computer, it might be invented and used by other civilizations or life forms. Is that at all how you conceive it?
Yeah, absolutely. I mean, I was trying to present science as a kind of a technology of knowledge production, and in some ways a black box. I mean, we're all inside the box, and yet that doesn't mean we really see what's going on in there clearly at all. So the idea was there was this machine that seems to work really well, but we don't fully understand exactly what it's doing. It's come along really pretty recently because I think of it. I think of modern science, just the science since the scientific revolution, as being its own thing, and really the book is all about that. And so the idea is this: we want to take apart this machine and figure out how it works, and maybe improve it, maybe decide just to better to leave it alone.
Mm-hmm. And I'm sure that what science, so this black box, as you describe it, is, or at least how we ought to think about it, will come out as we talk. But what's so fascinating at first blush is the history, because we've had, I mean, the same cognitive faculties for hundreds of thousands of years or so, but science as we know it has only been around, like you said, for a few hundred years. And being in a philosophy department, you know just how brilliant people like Aristotle or Plato were, and countless others over the couple of thousand years between them and us. But so what then do you see as some of the basic limitations that prevented their adoption or discovery, depending on how you want to look at it, of the tenets of modern science?
Well, I guess the twist in the book is really that it wasn't Aristotle who had the limitations. It's modern science that has the limitation. But it's a limitation that actually unleashes a lot of power. So the limitation in question is modern science's insistence that at least in its public communication, so in journal articles and so on, scientists do everything by way of empirical reasoning. Okay? So Aristotle didn't feel he was limited in that way. He cared a lot about observation, and in fact, as far as we can tell, he devoted a huge amount of time to careful observation, especially in his work on biology and so on. But he also, of course, is a philosophical reasoner. He wants to tie it all together and have it make sense as a kind of a synthesis, a harmony, and that's really important to him. Something that we as philosophers especially, I guess, appreciate about his work. But it also, I think, didn't hold him back exactly, but it held the investigation of nature back. Not in a way that anybody at the time, that Aristotle, or for that matter, so many natural philosophers who came after him, like the the scientists of the Islamic Golden Age or the Chinese scientists and so on, in ways that they couldn't possibly have foreseen. It was almost like we had to stumble into this idea that if we just limit our investigation, or really in a way, limit our communication of our investigation in a certain way, in a way that, as I put it in the book, is actually irrationally narrow, that will have this salutary effect. It will kind of engage the motivational gears of the human psyche in a way that will turn up stuff that, as I say, nobody could really have foreseen, but which has turned out to be just incredibly powerful in its ability to help us to uncover the way that things really work.
Mm-hmm. It's surprising that you would think that the desire for a synthesis, as you put it, held back our understanding of nature. In what ways is this the case for Aristotle?
Right. Well, I think, you look at, I mean, there's of course, there's a lot going on in Aristotle's approach to thinking about the way the world works, but he's most of all concerned with explaining the qualitative properties of things. I mean, not purely qualitative, but what he isn't doing, I suppose, is something that Isaac Newton in particular did do, which is try to write down some principles, some mathematical principles that get the motions of objects exactly right, that kind of zero in on precise details. And why does Aristotle not do that? Well, I think it's because he really wants to understand the big explanatory principles, and he thinks the little details aren't what's going to tell you about the little explanatory principles. Whether something takes 2 seconds to roll down an inclined plane or 2.1 seconds. You're not going to get to the fundamental explanation of gravity by making measurements like that. You're going to get to it by thinking about all the different kinds of ways that gravity exerts influences on things, trying to see what they have in common and trying to tie it into even bigger principles about change and matter in general. That's short, inadequate, but I hope helpful summary of Aristotelian method with physics, at least. What we, in effect, had to discover, and I feel there's just absolutely no way to see this in advance, that at least in the kind of world we live in, it's actually much more effective to do what Newton did, and to some extent also Newton's predecessors like Galileo, but Newton is the great exponent during the scientific revolution of this method, to really try to get those numbers exactly right. And it's by getting the numbers right that the doors swing open to much deeper insights into the way everything works. Of course, not right away. I mean, Newton died not knowing much more about the fundamental causes of gravity than he did at the beginning of his life. This process sometimes is unfolding over hundreds of years, not just a few years. But the thing that really made modern science into the knowledge machine, something that can not only give us a lot of really useful practical knowledge, but also insight into how life and physics and so on, matter, space and so on really work. The thing that's really powering it is these very precise empirical observations. And what we needed was a really a fundamental turn away from that qualitative explanation-driven way of thinking to a way of thinking that is much more based on in effect getting the predictions right. And that's what I see as the fundamental achievement of the scientific revolution is discovering that the Newtonian method worked so well, and then institutionalizing that method so that not just in physics, where relatively speaking it was easier to apply, but across all the sciences, people tried to do much the same thing.
I'm going to focus on this word method that you just said a number of times. So hopefully we'll get back to Newton and the history. But what I'd like to start with is what you refer to in the knowledge machine. I'm not sure if this is a canonical phrase, but the great method debate, and relatedly, of course, empirical observation. So in the introduction to the book, if I have this right, you describe science as an alien thought form, which I really liked. But Can we start by talking about the framework of the scientific method and what makes it so different from our more intuitive ways of thinking? And sorry, before you go on, I'll flag right here for you that this, or for our listeners, that this is a contentious issue. So maybe at this point we can start with the scientific method that everybody's taught in high school, the textbook version, before getting into the debates about it.
Yeah, sure. So it's true that if you ask a randomly selected philosopher of science these days what the scientific method is, they're quite liable to say there is no such thing as the scientific method. You go to those textbooks, you go to the high school exposition of the scientific method, and what do they say? They say, well, scientists formulate hypotheses and then they conduct experiments, and those experiments they conceive of as tests of the hypotheses, and in the light of the experiments, they become more confident in some hypotheses and they dismiss others. All that is, of course, true, or it's not always experiments. Sometimes it's observations and so on. But that is absolutely correct. So it's not as if the textbooks got something wrong exactly. What is it then that philosophers of science mean when they say, "Oh, there is no scientific method"? Well, I think they're exaggerating maybe a little bit. But I think what let's say about 100 years ago, when the philosophy of science really became a thing in itself in philosophy and not just something that scientists wrote about in their spare time, the big question about scientific methodology that was framed was not a question about that would be answered by these textbook presentations. Scientists formulate hypotheses, conduct tests, and so on. That was taken for granted. The question is rather, can we write down a kind of in an inductive logic of science that will tell us how to interpret the experiments? That is, how to bridge that gap between looking at what your experiments or measurements have provided and deciding what to do, what to think about your hypotheses. And when philosophers say there's no method, I think what they mean is that there's no regimented, objective, logic-like system for doing that. So to summarize, there's various ways of various expectations you could have of something that you might call a scientific method. For some of those expectations, just tell me what a typical scientist does on a typical day. Well, they probably write grant proposals actually, but at least in the idealized science, there isn't a perfectly good answer to that question. But it's not everything that the philosophers working on confirmation and the scientific method and so on in the 1920s, 30s, 40s, 50s were looking for. That's, I guess, part one of an answer to that question.
Maybe it's also worth noting for the moment that philosophers of science also disagree about this textbook high school scientific method description, because different sciences employ very different methods. So, for instance, I think you note in the book that astrophysics, or maybe it's cosmology, or astrophysicists or cosmologists don't really use experiments. And I think this led the late Ian Hacking to dispute whether it was even a science at all. So, but maybe we should start with one of those early philosophers that you're referencing, Karl Popper. So how did he conceive of the scientific method?
Right. So Popper is one of these. He's working in the 1930s and 40s and 50s, or flourishing then. That's when he's really putting together his story. He's trying to give a story that goes beyond just this idea that scientists do experiments to test hypotheses, to explain the logic of that testing. And Popper is famously skeptical about induction. So he doesn't just acknowledge that Hume made a good point about our inability to come up with some logical justification for induction. Popper actually thought that there was no good justification for induction, and that if science was going to be a respectable thought form, it would actually have to dispense with inductive thinking. So he came up with his now famous idea that science is all about falsification. you can't get together evidence to establish a hypothesis. That would be inductive argument. But what you can do is get together evidence that refutes a hypothesis. What science is all about is refuting as many hypotheses as possible. Whatever's left standing, those are the remaining candidates to be the truth. But we can never really say a whole lot more than that. But what that picture, which is controversial, and I think not too many philosophers of science anymore would subscribe to it. But that picture has a certain virtue to it of laying out exactly what I was saying. Philosophers were looking for a kind of a logical principle that anyone could follow. You just look at in effect, you look at the predictions and you see whether they're logically consistent with the hypothesis or not. If they're inconsistent, the hypothesis must be false, and you go along in that way. In some sense, if it were really that simple, scientists would never really disagree about the results of experiments. They would just, unless they were logically confused. Of course, they do disagree, which is one of the reasons that people think Popper oversimplified it a little bit.
Another virtue, though, I think of this falsification view, even if it's not dogma, even if it doesn't successfully demarcate science from pseudoscience, is that it does still serve as a normative ideal to which scientists can strive. They shouldn't be just seeking to confirm their hypotheses. It's a good idea to seek to disconfirm them or refute them. But moving on then from Popper, another very famous philosopher of science who I think weighed in on this and changed the way we think of the scientific method is Thomas Kuhn. So where does he fit in then in this lineage of scientific method discussions?
Well, Popper, at least Popper's starting point was to make to deliver what philosophers wanted, which was to make logic the starting point of any story about the way evidence works in science, the way that empirical testing works in science. And Kuhn's greatest contribution is to suggest, I think, that we need to do something that I, in fact, do in my book as well, which is look at sociology and the psychology of scientists as well as logic, that we won't really understand what's going on unless we think of science as a kind of sociological system, as something that's as much concerned with motivating scientists as with giving them some logical principle to follow. So that I think in the abstract is Kuhn's greatest contribution. He's most famous for talking about scientific revolutions when there's some dramatic discontinuous change in the kinds of theories that scientists are on the whole owe their allegiance to. So, for example, the shift from Newtonian physics to Einsteinian physics and to quantum physics, that's a revolution. It's not as if there are people running through the streets throwing Molotov cocktails, but still there's this dramatic overthrow of the old picture and a new picture rises up to take its place. Kuhn is famous for saying that process is not guided by logic. But in a way, he was already saying that none of science is exactly guided by logic, at least not in the sense of a kind of timeless objective principles that all of us, including Aristotle, can agree to. Rather, there's a kind of a systematization of science that Kuhn thought is very important, but which is much more a matter of something more like a subculture than a logical system. So he used the very famous word paradigm to refer to this thing. And his idea is that at any time, any domain of science or subdomain is governed by a paradigm, which means that there's a whole set of principles, ways of doing things, set of priorities, and so on, that scientists at the time conform to and take on board and use to do their science. And Kuhn thinks it's the reason that science works so well is not so much that these little, or rather, well, big and yet very, very confined in historical terms. They may exist just for a certain time in a certain place. These little things, the reason they work so well in regulating science is not that all of the principles that make them up are somehow correct or logically impeccable or anything like that, but that they create a kind of a microclimate for scientists, which is so psychologically secure that scientists feel motivated to do the kinds of often really expensive, time-consuming, effortful, and risky, at least in terms of wasted time, experiments, measurements, observations that turn out to provide these little measurements that I was saying a few minutes back are so important for the progress of science. So Kuhn really there was saying a bunch of connected things, which I think are really insightful. We need to look at the sociology, the motivational force of what's going on, and the objective validity doesn't matter as much as the ability of the system to push scientists to do things which, as he put it, it's hard to imagine them doing otherwise. So in a way, that's, to me, you can tell I'm kind of quite inspired by Kuhn. A big part of the knowledge machine is this kind of motivational machinery, this creation of a secure intellectual climate. Well, it turns out when a scientific revolution happens not to be so secure after all, but secure seeming intellectual climate. That's what really gives the scientists the confidence they need to throw themselves wholeheartedly into making these often very kind of tedious, time-consuming measurements that certainly Aristotle thought would be, for the most part, a waste of his time to make those measurements. And, even if they don't get to see the good consequences, to ultimately bequeath them to science and to crank the handle of the knowledge machine a few more times.
To recapitulate just a little bit and make sure that I understand. So we agree that there's this systematization of science around culture, and that revolves around the concept of the paradigm that he introduced for the philosophy of science. But then the psychological security aside, which I know is as you mentioned, is important for the knowledge machine, is it right then to think of the paradigm as dictating the scientific method for a culture? Or on his view, is there still a scientific method that operates independent of the paradigm, or is he one of the no scientific method people at all?
In a way, he's the I guess I shouldn't say paradigm, the paragon of no scientific method. I mean, of course, he wouldn't dispute the picture in the high school textbooks that scientists formulate hypotheses and conduct empirical tests of those hypotheses, and that they're interested in theories that have that are building models that are good at prediction and so on and so forth. So it's possible to in that kind of breezy high school way write down a few paragraphs, sort of thing that ChatGPT will give you if you ask it about the scientific method, that characterize something that all the different subcultures of science have in common, that all the different paradigms have in common. But Kuhn thought that a lot of what was most important in guiding a scientist and telling them what to do every day when they turn up at the lab or the observatory or whatever, is stuff that's always specific to a particular paradigm. The way actually Kuhn put it in a quite inspired, quite extreme metaphor was, it was almost as though the paradigm turned science for any particular, a scientist, the paradigm for some particular field turns the scientists in that field into puzzle solvers, as though they're being presented with something like a crossword puzzle or a Sudoku or something like that, where the rules are very clear, the framework is very clear. It's just a matter of trying as hard as you can to follow the rules and get the little bits into the right places. So it takes something that's completely open-ended, the study of the universe, as, say, Aristotle again would have conceived it, and turns it into this extremely concentrated, extremely regimented, extremely rigorous by local standards exercise in the application of intellect, and also just a lot of labor to get the little pieces to fall exactly into place. Kuhn thought that for the average scientist, that was actually a lot more motivating than some big conception that would be great to explain how the universe works. The kind of human delight in solving a puzzle, but also the kind of the the sweetness of knowing that the rules have been set, that there's definitely a solution to the puzzle, all of that conspires to push scientists to do this stuff they wouldn't otherwise do. That's so important to modern science.
So I'm sorry for banging my hand on this, but I just want to make sure that I have it straight, that he's in the no method camp, in the sense that you mentioned earlier, that he would say that there's no determinate way of moving from data to interpretation.
Yeah, that's right. So every scientist has a method which comes to them from the paradigm, but there's what the different paradigms have in common is something that's nothing, but is too vague to count as the kind of scientific method that people like Karl Popper and many of the 20th century philosophers of science were looking for. So Kuhn, more than anyone else, has inspired philosophers and also historians and social scientists to say, look, there is no scientific method.
Okay, and I find the scientific method stuff very interesting. So thanks for bearing with me. This is the last thing I wanted to ask about the great method debate. But you mentioned that, like Kuhn, you think we ought to look at the history and the sociology of science to evaluate the scientific method. But one sociologist of science that you reference, Stephen Shapin, I think is his name, he argues that there's no such scientific method. And is it for similar reasons to Kuhn, or is it a different sort of argument here?
No, with Shapin, I mean, he famously says there was no scientific revolution. So there was no point at which people suddenly started doing things differently. I think he's wrong about that, although I agree there's a lot of continuity with what came before. But he is, he would certainly be happy to say that there's not the univocal scientific method that the 20th century philosophers were looking for. And he would also be happy to say that there are a lot of social factors that are really important to making science successful. I suspect he would be suspicious of my claim that there's one single thing that has been supremely important ever since the beginning of modern science. But he himself has done a lot of interesting work on what these social factors have been over the ages. For example, perhaps some of his most famous work is about the importance of a kind of a trust that early scientific, and this is in the 17th century, had of one another's observational reports because they were coming from other gentlemen in the upper class sense of the term.
Well, I'd like to move now into your characterization of science. So what does it mean when, and we've hinted at this already, but what does it mean when you write that science doesn't give us a system for eliminating human thought from science? It's not some sort of algorithm, but that it tells us what counts as evidence, and it sets rules for how scientists can conduct disputes and debate.
Mm-hmm. So what those philosophers who were looking for the method were after was like people like Popper, was an objective logic. Scientists, of course, as you were saying earlier, have all sorts of. Scientists are people too. They're more likely to look favorably on their own theories, on the theories of their graduate school advisors, of people who are using the same methods that they learned in graduate school or when they were doing their postdoctoral research and so on, and so forth. We could talk all day about the various kinds of motivated reasoning that scientists are apt to engage in, just like anybody else. Now, the objective logic of science would be, if it existed, would be something that would keep all of that humanity out of scientists' reasoning, at least when they were doing the most important thing of all, which is assessing the weight of evidence, deciding whether this piece of evidence is really good evidence for some theory or really good evidence against the theory. So they'll, just as the rules of addition keep our prejudices out when we do mathematics, so the rules of the method would keep our prejudices out when we weigh the evidence. If there is no such logic, as I think, so many of us now agree, which isn't to say there are no rules or norms whatsoever, just that the norms are not constraining enough to compel agreement on what the evidence says. So in other words, it's possible to have a whole range of scientists who are all following the norms as far as the norms go, but who still disagree strongly about what the evidence shows, because maybe for one of them, such and such a method is the gold standard for evaluating a certain kind of hypothesis. For another one might be very suspicious of that kind of method. They simply have that kind of disagreement as long as the science is alive, and no logic of science exists to adjudicate in that particular case. So you get real disagreement. Okay, then. So what do you get? What kind of agreement do you get? As you get agreement, and now I'm coming back to your what you asked me about, agreement on what constitutes an empirical test. Not on how to interpret the results of an empirical test, but just what counts as a relevant empirical test. What would be a good experiment to do in principle to test such and such a hypothesis? Or I should say, maybe I shouldn't have even said what would be a good experiment, but what would be a legitimate experiment? What would count as a legitimate empirical test? What would count as actually subjecting this hypothesis to the one way modern science has of actually discriminating between theories? So they can agree, okay, we could do this experiment, we could do that experiment, we could get this data, we could get that data. They're not going to agree on the significance of that data, but at least they'll agree that they're all doing science. So there's a kind of a unity to the project, which distinguishes science from some other forms of thought, perhaps philosophy, or at least philosophy as a whole, that allows different scientists to go on doing the kinds of things they do. As I say, some of them will not entirely discount, but take what other scientists are doing with many, many grains of salt. But as long as they're all continuing to do their empirical work, the evidence is piling up. And as the evidence piles up, it gets, on the whole, easier. I mean, there are no complete certainties with this stuff, but on the whole, it gets easier to see which things are really working out and which aren't. So there may be a lot of dispute about some early experiments, testing some hypotheses. I talk a lot in my book about some of the early attempts to measure, in the wake of Einstein's general theory of relativity, early attempts to measure how much gravity bends light rays. And there was real disagreement on exactly how good the data was. But everyone, without ever resolving those disagreements, I mean, in some sense, they're still not really resolved. People just continued. The very people who are arguing with one another continue to do more measurements and more experiments. And after a while, the data just really started to stack up one way rather than the other. Various complaints, objections, doubts that were raised for one set of measurements are resolved the next time around because, well, sometimes just because conditions are better. Scientists get lucky. And so you get the evidence beginning to point in a particular direction after all. But it's never the case that scientists are agreed on what particular pieces of evidence show. It's rather that their disagreements are kind of washed out by the total volume of evidence. Again, it's not a certain thing, but on the whole, historically, this is what's happened.
So the rules of science, this focus on basing claims on evidence, even if there is dispute about the significance of specific items of evidence, it prevents appeals to religion or aesthetics or unfounded intuitions in arguments. And is this what you see as having sparked the scientific revolution?
Yeah, but it's important to qualify that in a certain way. So it's the rules of modern science, what I call the iron rule of modern science, is all about public scientific communication. It's about the way scientists argue in their official channels of communication, mainly scientific journals, sometimes conference papers and so on. And in those journal articles, all you can do to argue for or against a theory is to supply empirical evidence. So that everything that goes on in the journals is about, actually, the stuff that the high school textbooks say it's about: formulating hypotheses, figuring out the consequences of those hypotheses, subjecting them to empirical tests, publishing the results of those tests, cranking through statistics, and so on, etc. And that's the only thing that's allowed in there. That's the great limitation that I was talking about a while back. But that in no way limits the way that individual scientists can think in their own minds. So it's not as if a scientist is limited in their own thinking about how to interpret the evidence to purely empirical concerns. For example, one example I use of a non-empirical concern, which is a little bit more contemporary than, say, talking about theological considerations, and maybe a bit more transparent than talking about philosophical considerations, is the matter of theoretical beauty or elegance. So a lot of physicists will say that elegance actually comes into their thinking when they evaluate theories, when they decide, for example, what looks like a promising theory, or one that just looks too much of a kludge to really take seriously. And these decisions have real consequences for the progress of science. So it's really important stuff. It's driven in part by these perceptions of elegance. That's the sort of thing that can't actually appear in the scientific journals. So you can't argue in the journal on the grounds of a first theory on the grounds of its elegance. You've got to front up with some actual empirical evidence, and this is really the importance of this restriction there, to get to the nub of your question, isn't so much that it prevents scientists from being subject to all sorts of subjective considerations, but rather that it pushes them, however they are subject to those considerations, to put their energy ultimately, if they want to make progress, into empirical testing. So it's much like Kuhn said, that what's really important about the scientific method is not that it provides a set of rules that's objective, that's going to get all scientists to at least roughly agree on the significance of the evidence. You don't get that. And I think you don't even get that in a sort of the small way that Kuhn thought you did with a paradigm. You get a lot of disagreement even within what Kuhn would have thought was the very same paradigm about the significance of different sets of data. But what you do get agreement on is just to keep producing the data, and you get great motivation to do that, because it's the only way to actually publish in science, and therefore to get credit for your ideas and to have a career.
Right. I mean, even within the current physics paradigm of quantum theory, I mean, everybody will agree on the data, but the interpretations of the data are very much up for dispute. But returning to what you said about the admissibility, at least in reasoning, if not in journals, of other sorts of concerns like aesthetics and elegance. This also, though, of course, has notable downsides. So I'm not a physicist, even though I just referenced quantum physics, but I know that there are a lot of criticisms of string theory and string theorists, that their extreme attention to beauty and using that as one justification for their research program has drawn lots of brilliant minds away from quantum theory, for instance, which has been testable and perhaps more successful by some metrics.
Or building models of sort of that somewhat more complicated physical systems around us, doing solid state physics, that sort of thing. So you get a whole lot of people who are just kind of lost in mathematics. Which was the title of a book by Sabine Hossenfelder, who's one of the critics of string theorists and other theoretical physicists' infatuation with beauty. I know so much myself take sides on this. Yeah, partly, but partly just to for professional reasons. I'm more interested in the way that beauty comes into physics and also at the same time stays out of physics. But there has been a trend. We're really just talking about a tiny little fragment of the scientific activity that's going on around the world, but a fragment that gets a lot of attention in the media and so on. This really, it's fascinating stuff, of course. The string theory, the early cosmology, notions of the multiverse and all of that. That stuff can start to look like it's no longer following what I call the iron rule. It's no longer being this discourse is no longer being empirically driven. It's no longer being formulated with a view to empirical testing, and instead starts to look more like the kind of thing you would get in Aristotle, much more mathematical, of course, but something that certainly is exciting and engaging and pushes a lot of good buttons. It's beautiful, intriguing, weird. It's, as a philosopher, it seems like great stuff, but it looks like it's straying outside the bounds of science as it's supposed to be done. Now, to some extent, that's because no one knows how to test these theories, or the kinds of obvious tests are just impossible to carry out because they require amounts of energy that we are way, way beyond our abilities to marshal. So, it's not as if people are neglecting empirical tests they could be doing. But people like Hossenfelder and other critics think that still it's kind of setting the wrong tone, and it is there is something unscientific about it. I agree with it. Not saying it's right or wrong, but there is something really unscientific about it, and as a consequence, it's missing some of that empirical energy, which is so important to making science work. Maybe it will turn out to have other benefits which are well worth harvesting. I don't know. But it's a good example. It's a good borderline case where you get to see scientists themselves doing what you don't usually get to see them doing, which is actually explicitly discussing the big rules, rather than just quietly following them, often I think without barely even noticing that they're there.
Mm-hmm. Yeah, there are all sorts of ways that unscientific concerns get involved in science. Beauty is one. Ethics or moral considerations dictate what goes on in a psychology lab. But one thing I wanted to ask, so you mentioned the iron rule of science a few minutes ago. I think if anybody looks at the book, I think there you refer to it as the iron rule of explanation. But just in a slogan or a sentence or two, what explicitly is the iron rule?
Well, the iron rule says in just a few words that only empirical evidence counts, or only empirical testing counts. As I say, you've got to follow that with a qualification in official scientific literature. So when you go to publish something in the journals, it's got to be all about empirically testing some theory. Either typically it will just be a bunch of data. It's not just that. There's also a shared understanding of what actually constitutes an empirical test, and that's important too. It's not something that would surprise you, but it's important that all scientists, however, even if they don't have an objective standard for weighing the evidence, perhaps, but they do have an agreement on what counts as empirical testing, and therefore they have an agreement on what the iron rule is actually saying when it says only empirical testing counts.
Yeah, I'm curious about this. What is the agreed upon understanding of what constitutes an empirical test?
Well, this is why in the book I do call the rule the iron rule of explanation, because I think it's all about explanation in a certain shallow sense that's often almost indistinguishable from prediction. So to test a theory, what you've got to do is take the theory, the hypothesis, whatever, put it together with some circumstances, and get the theory to say something about what will be observed in the future, or what would have been observed in the past, or just get it to tell a story that you already know. That is, to tell a kind of explanatory story using its fundamental causal principles about why something happened the way it did. So an example of that would be where you have a model in evolutionary biology that shows you how some particular trait evolved by natural selection, for example. So more of an explanation than a prediction, but one that still works in a prediction-like way. You have the model with its principles, you crank the handle of the model, and out comes the story. So anything like that is an empirical test. But the basic idea is what you do is you go to and I think there are always causal principles of a theory, and add the circumstances, the background conditions or whatever, and get the theory to say something about what will be seen or what was seen, and then see whether that actually matches reality. And that's an empirical test.
And so we've talked about some of the, I don't know if you want to call them caveats to the iron rule of explanation, but for instance, the allowance for subjectivity and thought rather than argument. But one thing that you note is that you call it the iron rule's fourth innovation, is that a theory is measured only based on how it accounts for observed phenomena. And we talked about aesthetics that can enter into our reasoning around the theory, but not in our defense of it. But so what were things like before this innovation? Is this where you have, okay, Galileo's theory can't be correct because we're measuring it against church teachings, and so it's just wrong, that sort of thing?
Yeah, that's an example. I mean, that's so. That's maybe especially for people with some philosophical knowledge who are watching, a better example in some ways just to look at what someone like Aristotle is doing in his physics. So there's a kind of there's not some theological doctrine that really comes in from the outside, which is kind of what's going on in the Galileo case. And in fact, as historians have argued, it was really more about the authority of the church than any particular factual doctrine, that whole dispute. But you look at Aristotle, and he wants his theory to account for the observable phenomena, but he also wants it to make sense as philosophy. So there's a kind of a fundamental theory of change. There's a fundamental metaphysics of form and matter. And maybe above all, there's a desire to have a kind of a deep explanation of why everything happens. If possible, now maybe this isn't really possible, but if possible, to have principles that are somehow inherently, immediately intelligible, and for everything to follow from those intelligible principles. You see the same thing much later with a philosopher like Descartes, writing in the middle of the scientific revolution, and actually with many other thinkers like Descartes, who insist on mechanical explanation. So it's very different from Aristotle. Here, the fundamental intelligible explanatory principle is one of collision. Things hit one another and they bounce off. That's something that that kind of motion is in Descartes and the many other mechanical philosophers, seen as something that can account and make intelligible everything else if we embed it in the right kinds of theories. So that I'm all thinking of as, in a certain sense, pre-scientific or pre-modern science. And the great contrast case here is someone like Newton. Newton comes along, just a few years after Descartes, and says, look, I don't know how gravity works. Maybe there's some kind of invisible particles bouncing off one another, or maybe there's genuine action at a distance. I just can't figure it out. But that's okay. I don't need to do that. In order to explain things like why the moon is going around the Earth and why there are tides and so on. All I need to do is write down some mathematical principles and derive the observed phenomena from those mathematical principles. Okay, so what's being left out here is this need for intelligibility in the explanation, some kind of a sort of a depth to the explanation that goes beyond just deriving something from principles and sort of gives you a sense of understanding from the ground up why things are happening the way they are. That kind of what I think we should think of now as a philosophical need is one of the things that's being excluded by the Iron Rule. It's saying just not only don't worry about that, but you can't bring that in. You're not allowed to bring that in. So, for example, with something like quantum mechanics, which many physicists have, with good reason, said is in a certain sense unintelligible, a paradox. It makes no sense. I think maybe Richard Feynman says none of that counts as a consideration when actually publishing the machinery of quantum mechanics of modern quantum mechanics from the 1920s onwards. Everyone may be thinking, how can this possibly? This isn't a reality that I can even understand. But nobody is, in a way, is allowed to say that. Einstein tried to say that, but he really failed to move people at all because he kind of stepped outside the bounds of science by saying it. And so because quantum mechanics works so well, because the models of quantum mechanics are so good at providing derivations of the things we see around us, and because that's the only thing that we're allowed to care about, or officially allowed to care about in scientific writing, all this intelligibility stuff is just off the table. So quantum mechanics just sweeps everything before it in 20th century physics, and with very little contention becomes the new doctrine, the new dogma of the non-gravitational part of fundamental physics.
It's funny that one of the basic goals of physics is to understand and describe the universe, but the more that we describe it, the more it becomes incomprehensible. Yet that's just fueled by the knowledge machine. But well, now that we've fleshed out what the iron rule of explanation is and it's fundamental to characterizing the knowledge machine, I'm curious about something that you said earlier, which is you think that scientific thought requires the suppression of the rational mind, that the iron rule of explanation isn't rational. Because from my present vantage point, and maybe it's because I'm just in the box, it makes sense to only be referencing data in a scientific paper and not to appeal to aesthetics or religious views or something like that.
Yeah, well, I suppose it depends on what you think the purpose of a scientific paper is. But if you think of it, and I think this is sort of the standard way of thinking about it, again, it's what you would get out of those high school textbooks. If you think of it as providing reasons for or against believing a theory, then because of the iron rule, what a paper is doing is it's leaving out certain relevant reasons. Okay. Now you might think, well, some of those potential reasons maybe are no good. So, for example, perhaps no kind of religious reasoning is going to be at all helpful in figuring out what the right physics or even the right biology or psychology is. So actually leaving that stuff out is good because it's totally unhelpful. But a lot of physicists, going back to the beauty thing, again, mainly because it's I think a particularly simple and clear case. A lot of physicists think that the beauty or elegance of a theory is a really important consideration in judging whether it's promising or not, whether it's plausible or not. And what the iron rule is doing is it's saying you can't bring that in a scientific paper. Okay. So if you think of the point of a paper as being to kind of assemble the case for or against a theory, then the iron rule is getting in the way of that process. And in that respect, I think, the iron rule is telling scientists to do something irrational, namely to leave out considerations that they think are relevant and important. So it's not the scientists themselves who are irrational. They bring beauty and whatever else into their thinking. Okay. And science as a whole works really well. So in some sense, science as a whole is not irrational. But the rules of this very particular game are irrational. If you see the game as being all about as I say, getting reasons together, reasons to believe or disbelieve.
And you didn't want to take a stance on whether it is in fact rational or irrational to take beauty into consideration for theory choice, right?
Yeah, well, I mean, you can, I do, and I'll say, I do in fact think that properly circumscribed, it seems that paying attention to something like beauty has been valuable in the past, and presumably will continue to be valuable. It has to be the right kind of beauty and in the right kinds of domains, but it does look to me like it has been valuable. But my main point is not to argue that case. I'm just more interested in beauty as an example of a thing that on the one hand, some scientists think of as being very important, and on the other hand, something that they're not allowed to bring in to their public presentation of their own reasons to believe. But in fact, they're being censored. They're being told it may not, then any official presentation of your theory or your data describe some of your perhaps most important reasons for believing the things you do. That's quite a remarkable thing, I think. Whether you want to call it literally irrational or not, it is very strange. This is why I'd call science an alien thought form.
Mm-hmm. And I'm sorry if I'm making you repeat yourself now, but are there other sorts of considerations beyond beauty that it might be rational for a scientist to employ in their thinking that the iron rule compels them to act irrationally and disregarding?
Sure. So some scientists do have religious convictions, and at least from their point of view, some of those convictions may be relevant to their science, but that's certainly excluded by the iron rule. On the more philosophical side, there's this demand for intelligibility. I mean, a demand of our inner philosophical selves for intelligibility. Now, maybe some philosophers are jaded enough to want to jettison that completely, but I think other philosophers really feel a need for that in theories and are not satisfied with a theory that doesn't go a little bit deeper than just a bunch of mathematical stuff that gets the data right. And that's a different kind of thing that is being excluded from scientific reasoning by the iron rule. There's also a whole lot of other stuff that maybe is, well, it's relevant. There are multiple reasons for not including it in scientific publication, like a scientist's impressions of say the reliability of some other scientist's lab. There's probably lots of good reasons why we shouldn't start turning the journals into an arena for airing suspicions about so-and-so's data. But those kinds of considerations are, I think, actually really important to scientists' thinking. So if you actually hang around with scientists, you'll hear them talking this way. It's not that they think there's a whole lot of fraud out there, but yeah, so-and-so got those results, but I wouldn't trust them too much. Whereas so-and-so's results, they're sure to be pretty solid. So these kinds of considerations all stay in the private side of scientific deliberation.
No, that was really helpful. So we're not talking about an ideal rational agent, because some might say a rational agent wouldn't have religious beliefs, but it makes individuals act irrationally given whatever beliefs they do have, regardless of whether from a God's eye sort of view we determine that they are rational or not.
Yeah, well, maybe it's important to put the emphasis on the act there. So it's not like the individual is irrational in their thinking, but it makes them kind of, as it were, act like an irrationally narrow exponent of their ideas when they actually publish their results in a journal. So they're acting out a persona that is fixated wholly on empirical reasons and ignores everything else.
Now, I wanted to finish by covering some things that didn't come up, and I just had a very general historical question. You said that Aristotle, I think, was more rational, and it wasn't until the 1600s that people like Newton became irrational, and this ended up fueling the development of the knowledge machine. But what was so special about 1600s Europe that brought the scientific revolution about, unless you think it was accidental in some way? We just had a couple of geniuses.
No, I do have I have a speculation that I spend a few pages on this in the book, that perhaps it had something to do with the settlements in Europe in the wake of the Reformation and the many religious wars, or at least wars that had important religious components that had unfolded in the late 16th century, early first half of the 17th century. That the way those wars were settled was, or at least the way that kind of religious divisions in Europe were calmed down, was through a kind of a compromise where people agreed, in effect, to act in a way that didn't necessarily always reflect their innermost thinking. So in one state to sort of to on the surface of things sort of go through the motions of conforming to the standard religious dogma, even if inside they thought differently. Now, of course, people have done that since there has been religious dogma, just in order to save their lives. But this was something a little bit different, I think, that you saw in the 17th century. You saw a kind of a institutionalization of these arrangements, and so a sense that there was actually something that made sense about doing things this way. It wasn't just a completely practically driven decision in any particular occasion to hold your tongue, but rather there's a kind of set of rules, a way of constituting society that in which what comes out publicly doesn't reflect what's inside. So you have in the kind of moral or religious sphere the same kind of division that I'm saying is crucial for the constitution of modern science. So maybe that the political arrangements created a kind of legitimacy to that framework that made it a lot easier for people to take on a framework like that. That made it seem like a way of doing things that wasn't just a matter of temporary expediency to be totally abandoned as soon as we get back on the road. We can all go back to being Aristotle, but something to take seriously and to as I say, institutionalize going forward. That's my speculation anyway.
Well, we talked about Isaac Newton a fair amount, but one other character in the scientific revolution that I wanted to hear a bit about was Francis Bacon. So how does he fit into and maybe exemplify some aspects of the knowledge machine?
That's a great question, I think, historically. So Bacon has come to be thought of in retrospect as a great harbinger of the scientific revolution. The book that did the most to earn him that title came out very early on, and what was it, around 1620, I think. And it might be possible to think, if you went back and just looked at the order of things, that everyone read Bacon's book, where he, in effect, says, let's just get together all the empirical data and make our decisions about what to believe based on the empirical data. You might think Bacon wrote down something that's a bit like the iron rule, and everyone came along later and thought, that's a good idea, let's do that. And then they started doing that, and modern science began. It's easy to to look at the story that way. I don't think it was really that simple, though. I'm not sure that Bacon really had a tremendous amount of influence on the thinkers who are most important in the scientific revolution. We actually have no evidence that Isaac Newton, in particular, actually ever read Bacon, although he did read other writers who were influenced by Bacon's empiricism. But there's no question that Bacon is kind of I think there's very little question that Bacon is sort of serving here as taking the temperature of an emerging culture of empiricism. I think that culture really remained more a kind of ideology, even in Britain, where Bacon and Boyle and Newton are all based in the British Isles, and that's what was always a place where the more empiricist ways of thinking were better ensconced, obviously in philosophy as well as in other ways. Yet, I think it's really only with Newton, who's doing his work from the mid-1660s onwards, that you get this idea we should just put everything in terms of a theory's ability to explain the empirical evidence, in the sense of just deriving the empirical phenomena in all of their detail down to the whatever decimal point, if you have data that's that precise, deriving it from the causal principles of the theory. That's the idea that really is all that matters. I think Newton is the first person to put that into action. Other writers before Newton, like Boyle, say stuff like that, but when historians have taken a closer look at what they're up to, they don't really seem to be following those rules very closely. But Newton actually, for whatever reason, and here you really are trying to divine the mysterious workings of one individual personality, for whatever reason, really took it seriously and did it, and of course was incredibly successful, creating the whole Newtonian theory of gravity in a way that got everyone, not just in Britain, but all over Europe, sort of sitting up straight and thinking, wow, I want what he's having. And that's, I think, when the iron rule suddenly came to prominence as a way that people were very seriously trying to do their science.
Well, I'm going to shift gears now to the future, the present from the past. And I've had a couple of conversations on the show about pseudoscience, one with another Barry Lower student, Craig Callender, who you probably know, and then also Massimo Pigliucci, who's just uptown from you at CUNY. But do you see actually, I'm going to ask a different question first. Popper's demarcation problem was supposed to help distinguish between science and pseudoscience. Do you see the iron rule of explanation as helping distinguish science from what is not science?
Well, it's certainly. I think the iron rule is essential to science. So it does lay down a fairly clear criterion that we can use that criterion to say this counts as science and this does not. And that criterion, at least for some kinds of pseudoscience, actually draws the line where you might think it should be drawn. So to take one very prominent example, the whole intelligent design movement, which was supposed to provide an alternative to evolution by natural selection as an explanation for the adaptedness of life, very much looks to me as something that does not follow the iron rule, that it created a kind of a discourse and that sort of system of journals and publications and so on that wasn't primarily concerned with writing down models that could make certain kinds of predictions and so on, but with something that was much more like a kind of a philosophically principled debate about the merits of evolution by natural selection as a theory. Now, in saying that, it's not as if a principled philosophical discussion is necessarily a bad thing. So it draws the line, but I wouldn't say that everything on the other side of the line is somehow suspect. There are a lot of stuff that's going on in philosophy of physics maybe is on the other side of the line, and it's good philosophy of physics. It may not be, it's not science, but it's still good philosophy of physics. So I don't see the demarcation line as being necessarily as doing the work of distinguishing respectable intellectual activity from not so respectable intellectual activity, which is, I think that's what Popper wanted to do. He wanted to say, look, either you're making falsifiable claims like real scientists, or you're saying stuff that just cannot be tested. And there's something really seriously wrong with that. Of course, he was, like a lot of the philosophers of this generation, he was a bit suspicious, not as much as some of them, but a bit suspicious of metaphysics. And one of the characteristics of the wrong kind of metaphysics is that it couldn't be tested. There was no way to actually adjudicate between different metaphysical theories. That would be a characteristic view of the time. Anyway, try and get back to your question. I'm saying, on the one hand, I do think the iron rule distinguishes modern science from everything else. And so it is a demarcation criterion, but it's maybe not the demarcation criterion that Popper was looking for, or that some other people are looking for, that would serve as a test that you could use to say, you people are not only doing something that's not science, but you're doing something that's just all out bad. I don't think it's going to do that work. I think to do that work, you will need to look at more particularly at the way that intelligent design theory is being done, or I don't know, the UFO theory or whatever, and see certain kinds of conspiracy theorizing, and find other things that are in a finer grained way are going wrong. So I'd like to, on the one hand, I'd like to advertise my views, but on the other hand, I think I'm not going to be able to help with many of these genuine problems.
Do you at all see the knowledge machine as under attack today? So whether that's by postmodernism or religious fundamentalists or conspiracy theorists or anything of this ilk? Because I think a lot of people perceive a sort of war going on in the culture between science on the one hand and everything else on the other.
Yeah, it would be hard to find people who are against science in all its forms, but there's certainly, as I think we all know, there are some political movements or frameworks or interests that find it very convenient from time to time to disparage large swathes of science, whether it's, COVID science or climate science or whatever. So there's a kind of a set of strategies for undermining chunks of science that are inconvenient in various ways. And in that respect, yeah, science is, as an enterprise, subject to, I think, some pretty serious kinds of attack. What's more, conventional understandings of the way science works often play into the hands of the underminers. So the underminers say, look, what happened with COVID? Scientists are supposed to be kind of looking at the evidence and objectively weighing it up. And then you look at something like the science of masking and nobody agrees on anything. Nobody agrees on which are the good studies and which are the bad studies, which are the important models and which models aren't telling you anything about COVID transmission. It's just a bunch of politically motivated actors all being manipulated by the great puppet masters in order to, who knows what, take away all our fundamental freedoms, I suppose. That story becomes easy to tell because people are expecting an objective logic of the interpretation of evidence, of weighing the evidence, something that really is not there. I would hope, maybe this is a vain hope, but I would hope that a few people would read my book and say, oh, I see now. Science works, but it doesn't work that way. The kind of the chaos that we saw with COVID, was of course not what we were all hoping for, but was kind of, that's what science usually looks like in its early stages. And it's it's not so bad usually. Of course, when you desperately need some kind of public policy to stop a pandemic in its tracks, it's a bad thing. But you can't have the impossible, and there isn't the kind of the objective logic of science you're looking for. So in other words, I would like people to be able to see, okay, we're not science is going to give us everything we want all the time, but the kinds of arguments or disputes we see in the science of masking or in climate science, that's just normal science. That's science the way it normally unfolds. That's exactly the kind of science that ultimately has gotten us our cancer treatments and our iPhones and all the other good things in life.
That's a very novel and refreshing way of putting it today, because usually you hear discussions of the mask controversies, etc., as the sign that science is failing us. So it's nice to hear that this is how science is supposed to work. But I've had a number of philosophy of science discussions on the show lately about quantum mechanics. So it was really great to talk about the basics, the scientific method, some history, and some sociology, all of which is in The Knowledge Machine in Abundance. So thanks so much for joining me, Michael. I really enjoyed this.
Yeah, this was really fun. Thanks for inviting me on your show. And yeah, I had a great time.